Space Nuts is taking a bit of a break at the moment. Fred and I will be back in the not too distant future with fresh episodes. In the meantime, enjoy some of the key episodes that we have presented over the years, major events in astronomy and space science. And we'll see you real soon.
Space Nuts.
Hi there, thanks for joining us on a Q&A edition of Space Nuts. I'm Andrew Dunkley, your host. Once again, thanks for joining us and good to have your company. On this edition, we're answering some questions about light in space. This one comes from Lee. He's asked a very interesting question. I've never actually thought about this particular concept, but it's a question that I think is worth answering for sure. That's why we included it. Fenton wants to know about shielding astronauts in the outer reaches of the solar system, and he's got an idea on how to do that. Robert wants to talk about things we learn from the moon, and what if our moon wasn't the same as the moon is now? Would our learnings be different? That's a really interesting question. And Duncan wants to talk about ice giants, and why are they ice giants? Why don't we call them something else? That's all coming up shortly on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Once again, we welcome the one and only Fred. What's an astronomer at large? Hello, Fred.
Hello, Andrew. How have you been since we last spoke?
I haven't moved from this seat in all that time.
Well, I can see you glued to your chair there.
Very much.
Am I, actually.
Very much so. Yes. Shall we get straight into it and answer some questions from our audience?
That's a good idea, yeah.
It is. That's what we're here for. This first one, Fred, comes from Lee. He lives in New York City. He's asking how much light is in space. He'll qualify that question. For example, if you were to visit Voyager 1, where Voyager 1 is today, would you be able to see it? Would you see just a silhouette? Would you be able to make out details and colours if there are any colours on it? What about if you and Voyager were midway between the Sun and Alpha Centauri? Can we know a reasonably accurate answer, or is it pure speculation? Thanks, love the show, Lee from New York. I've never thought about that. I mean, we take for granted light on Earth because we're illuminated by the sun, but it's a bit different in other parts of the solar system and the universe in general. So, yeah, if we could just go snap, we're out there next to Voyager 1, could we actually see it? Is it illuminated in any way? Is it being illuminated by something? What would it be like?
The answer is yes, you'd see it. So we're talking really now about the sensitivity of the human eye, because with a camera, with long exposure settings and things, you'd be able to see it in great detail. But thinking about the human eye, so I used to work, as you know, at Siding Spring Observatory. I spent many hours outside at night there. It is a place that is truly dark. There's no interference from street lights. There are a few blobs of light on the horizon, but nothing that affects the pristine darkness of the night sky. And on a starry night, with the sun not in the sky, you can see quite clearly. There's enough light from the stars themselves to let you see where you're going, let you, walk around and be quite confident that you're not going to fall off the mountain, as I nearly did one night when it was cloudy. I went out without my torch and thought, oh yeah, I'll see by the stars. But unfortunately, the cloud had come in. I couldn't see anything, and I nearly fell off the mountain. I didn't in the end, but
that's a long drop, Fred.
Yes, it is. Yes, it's quite a long drop. Anyway, if you, normally on a starry night, you will see by the light of the stars. Now, where Voyager is, Voyager 1, I just looked it up. It is at a distance from the sun in astronomical units, which is 163 astronomical units. That's 163 times the number of times the distance between the Earth and the sun. So That's 150 million kilometers. Multiply that by 163, and you will get. What do you get? I was looking for it in kilometers, but it's not there. I'll have to do the numbers. Anyway, it doesn't matter. The main thing is its distance is 22.55 light hours away. That's how long it takes the signal to get from Voyager to Earth. It's almost a day. It's almost a light day away. So at that distance from the sun, 160 odd astronomical units, there's still significant light coming from the sun, not to mention Venus and Jupiter and the other planets. Mostly the sun, though. You're being illuminated by the sun, so that certainly ups it as compared with just being illuminated by the starry sky, which is what I was just talking about. So you'd see it really clearly. You wouldn't have any problem making it out, assuming your eye was dark adapted.
So it's fairly bright out there. I mean, we talked about the sensitivity of the human eye, as you referred to. How small amount of light can we see as human beings?
I think there were some experiments. Let me think.
Was it 1 photon or 1 pixel or something like that?
There was. That's right. We might have talked about this. There were experiments done that showed that the human eye is capable of detecting single photons. It was under special circumstances, but and that is just extraordinary. When you think that the human eye can also cope with broad daylight, that's the amazing thing about the human eye. It can, it's quite happy to see light at one brightness and then a light that's only a millionth as bright. It's fine. You can deal with that. And that's a combination of what's called retinal bleaching and the iris of your eye opening and closing. It's all those things come together to give you this unbelievably versatile and sensitive tool with which we can look at our surroundings, whether it's the rock face I'm looking at now, because that's what our backyard consists of, or whether it's the night sky where you're looking at faint objects in the sky. It's quite amazing.
So even if you went deeper into space, way beyond our solar system, you would probably still see objects that you were near.
There'd be enough light from the stars. The Milky Way is bright. It would even if, as Lee says, even if you were halfway between the Sun and Alpha Centauri, you'd still see it because of the ambient light that's coming from the stars.
Yeah, and you'd still see colour because that's if it's dark enough, it might turn into the greys, which happens at night.
That's right. Yeah, and I think that's likely. I don't think you would see colour. You would where it is now. There's enough light coming from the sun that you'd see colour, but I think when you got further out, you would start to just see the as you said, that sort of pale grey appearance where you're looking at very low light levels indeed, where the colour cells aren't receptive.
There you go, Lee. The answer to your question is yes to all of the above, basically.
Yeah.
Good question. Great question. Excellent question. All right, let's move on. This is from Fenton.
Yeah, hello, Fred and Andrew. This is Fenton contacting you from St. Paul, Minnesota in the U.S. I sort of have a different type of astrophysical question for you. And this is on how to shield astronauts from radiation outside of the Van Allen belt. I was curious if you know of any pending technologies that would allow this. Obvious choice some people would say is lead, but I can think of several reasons why this is not a good idea. How about a miniature Van Allen belt, which could surround a spacecraft? How does that sound? How could this become a reality? Thank you very much. I hope you liked the question. Bye now.
Thanks, Fenton. Fenton always has these intriguing thoughts I've noticed in the times that we've heard from him. Maybe we should start by explaining what the Van Allen belt is for those of us who just can't remember, like me.
It's so the Van Allen belts are basically the magnetic shielding around the Earth, which is caused by the magnetism of the Earth. It's caused by the fact that we've got an iron core, and basically it's in two parts. It's solid and liquid, so it acts like a dynamo. It's rotating, and that gives us this exactly the protection that Fenton is talking about. I was going to refer. I'm a bit annoyed actually because I've lost it. There is a very nice article on. It's actually on the BBC's website, their Sky at Night website. There's a lovely article on exactly this. Here it is. I found it. I hadn't lost it. How astronauts can hide from radiation on Mars, and it goes into exactly the problem that Fenton's talking about. How do you prevent astronauts basically becoming irradiated, and over time it's basically lethal because of the cosmic radiation that's coming down through space, and it does cell damage in your body, and it can actually trigger cancer. So the whole study of this is, the thrust of this article, BBC Sky at Night magazine, is to discuss how you might protect astronauts from the radiation, and that's not just on Mars but en route. The solution that Fenton has suggested is covered in a paragraph. I'm going to read it because we quoted where the source is. For example, all right, let me go back a paragraph. One method of helping astronauts to avoid the radiation on Mars is active shielding. For example, superconducting electromagnets could be used to create a powerful magnetic field to deflect the incoming charged radiation particles away, just as the Earth's field does. That's the Van Allen belts. The problem is that such solutions can demand a lot of power to run, and the technology is a long way from being fully developed. An easier alternative is passive shielding, simply placing a thick bulk of shielding material between the crew habitat and the sky. And then they go on to consider different materials. Aluminium, aka aluminum, the metal that spacecraft are constructed from, is actually a pretty bad radiation shield. And they say when hit by an energetic cosmic ray, its atoms can shatter and fly onwards to create even more radiation particles. And Martian soil, the regolith, which if you're on Mars, you might think about digging a hole there. It's got the same problem, but it's actually, abundant. And so you could use that to dig a hole. If you put a 2 to 3 meter layer on top of your habitat, then you'll get some protection. But the thing that surprised me, Andrew, is, once again, it comes from this same article. Hydrogen is the best shielding material, as it's light atoms. Yeah, it's light atoms, and by light I mean not heavy. Its light atoms don't create as much secondary radiation, and so tanks of rocket fuel or water, which is rich in hydrogen, placed over crew quarters could double up as effective radiation shields. I've heard that before, that one way of protecting your spacecraft as it flies to Mars is put it in a tank of water. It's the last thing you'd expect to do, but water is a good shielding material. And they also point out the alternative of hydrogen-rich plastics like polyethylene could be used to cement regolith grains together. This is on Mars, and improve their shielding effect. So if you want to read more about this, it's an article that originally appeared in the August 2022 issue of BBC Sky at Night magazine, and it covers pretty well most of the ideas that have been suggested for this radiation issue. It's one that's got to find an answer soon, because good old Elon and his Starship is getting nearer to thinking about going to Mars. I don't think it's ever going to happen, but that's something he'll definitely be thinking about.
Yes, indeed. Oh, he's too busy dealing with the Australian government at the moment.
He is indeed. That's right.
Over some of the content on Twitter that the government wants to get rid of. simply because of its volatility. But anyway, that's a different story. But there's plenty of water on Mars, so maybe creating those water barriers is probably the simplest thing to do. You've already got the material there.
If you've landed in the right spot where you've got permafrost or whatever.
That's the question. Yes, indeed. Well done, Fenton. You actually happened across some of the answers too in asking your question. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
3, 2, 1.
Space Nuts.
Now, Fred, our next question comes from Robert. Hi, guys. Love your show. Sorry for the long question, but feel free to paraphrase or shorten it. Our moon is heavily cratered and has given us a lot of insight into the history of the solar system and perhaps how the planets formed. But what if we had a moon like the icy moon Europa or the shrouded in haze Titan, both of which don't show immediate evidence of cratering? Would our theory about how the planets developed would be different? What other insights about our solar system would be missing, or would we be missing? And lastly, would we have sent people to land on such moons, i.e., would they be more dangerous for astronauts? Cheers, Robert in Vienna, Austria. Wow, I don't think we've had a question from Vienna before, have we? Lovely to hear from you, Robert.
I think Robert might have been in touch once before.
I might have been too. Yeah, it's very rare to hear from Vienna.
Yeah, I was in Vienna at the beginning of last year, and I think we got something around about the same time, and I was waxing lyrical about being in Vienna at the UN when I was at the COPWAS meeting. Anyway, that's another issue. What if we had it's a really interesting question. What would we not know about the solar system if our moon was basically one that had been resurfaced in recent years or recent millennia? Because that's what makes a surface smooth. That's how we recognize the fact that it's how we recognize the age of a surface is by how many craters it's got. The older the surface, the more craters it has. And so the moon's southern region, which is heavily cratered, as is the backside, tell us that early on in the solar system's history, it was a very wild and woolly place with things charging about all over and causing these craters. Now, if we had a moon that was like Europa, that had, icy geysers on it that basically covered up the craters, would we have known about that? My guess is yes, we would, because we'd see other bodies within the solar system, like, other moons, like places like Ceres, the biggest of the asteroids, the dwarf planet that dominates the asteroid belt. That's heavily cratered. Parts of Pluto are heavily cratered. Mimas, one of Saturn's moons is heavily cratered too. So we'd know about it by looking at other objects, even if our own moon was smoothly surfaced. But Robert's last point on this, would we have sent people to land on such a moon? I think, I don't know. That's a really good question. I mean, we have sent people to land on our moon as it stands, with an ancient surface. In fact, where they landed were more recent than the heavily cratered surfaces, because they were principally in the Maria, the basalt plains. Yeah. So maybe that suggests that we would have landed people on Europa as well. Because
I think we probably would, because it would have a solid surface. There'd be places, because it would be so close to us, we'd be able to examine and find the right landing points. Might be a bit more difficult with a moon that's shrouded in layers of gas.
Yeah, that's right. And especially a place like Titan. I still think we'd have done it, actually. I think, the JFK's promise to put astronauts on the moon would have still held good, even if it had been a very different place. If it had been like Io, it might have been a different story where, you've got the most volcanically active body in the entire solar system with stuff going off all over the place. I think we might have been a bit more reluctant to land on Io.
Yes, possibly so. But it would be interesting to have something different. But then, if we'd always had, if we'd always had an ice moon, we probably would have got a question from Robert asking, "What if we had a rocky moon? Now, would we know? Would we have a different interpretation of the formation of the planets if there was a rocky moon next to us instead of an ice moon?" Yes. In an alternative universe, Robert, you would have flipped your question. Good to hear from you. Hope all is well in Austria. Our final question for this episode comes from Duncan.
Hello. So Duncan here from Weymouth in the UK. Again, a quick question. I was just doing some reading, and I noticed that Uranus and Neptune are often referred to as ice giants. Now, given that ice is basically just sort of like a rock form of water or CO2 or whatever else, but basically just the solid form of it, why are they not just called rock giants? Why do we make the definition of ice rather than just calling them rock? It just seems odd, because the little planets in the inner solar system are referred to as rocky planets. So given that they're also apparently rocky, why are they not called rocky giants? Okay, thank you. Bye.
Thanks, Duncan. Appreciate your questions as always. Why do we call them ice giants, just for the sake of the exercise? Because there's gas giants and ice giants.
Yeah, except one is a subset of the other. And so all four of the outer planets, Jupiter, Saturn, Uranus and Neptune, they're all gas giants because they have high mass, much more in the case of Jupiter, certainly, than our own planet. They're giants, they're big, they've got high mass, and they don't have a visible surface, which is why they're called gas giants, because all we see is a gassy envelope. Just to go to the last of Duncan's questions there, we wouldn't call the inner planets rocky giants because they're not giants, they're kind of normal planet size. You know, if you think of the Earth as being your standard planet, then Mercury, Venus and Mars are similar in size. They're all smaller. Venus is about the same size, but Mercury and Mars, of course, are smaller. So it's only when you compare with the size of Earth that you'd start talking about giants, because they're much, much bigger than Earth. And so that's the gas giants. So why are Uranus and Neptune called ice giants? Because they have hazes of ice in their atmosphere. So, and that's the trick. It's not a solid surface. It's not rock. It's a haze. It's kind of like a dust of ice which permeates their atmosphere, and it's water ice, in fact, mostly. So that's why they're called ice giants, because unlike Saturn and Jupiter, which don't have these hazes, the two outer planets, Uranus and Neptune, do. They have ice hazes in their atmosphere, hence the name.
Okay. Yeah, and of course, the last episode we learned there wasn't much water in Jupiter's atmosphere.
No, that's right. That's
right. In the two outer gas giants, yeah, it sounds like there is. Is that why they're a different colour?
Yes. Yes, I think that's right. They're and also their atmospheric constituents are different. They don't have the same belt structure that Saturn and Jupiter do. It may be that that's because any belts that exist are much lower in the atmosphere, and so you don't see them. Yeah, I mean, there's a strong body of advocacy within the space fraternity to get more spacecraft out to Uranus and Neptune, because they're the two planets about which we know least, and will be good to know more.
Yeah. Well, if you sit down in snow for long enough, Uranus turns into an ice giant. I couldn't help it. Sorry. Yeah.
Which is why we call it Uranus in polite circles.
Yes, I know. Yeah, but it's just a joke you've got to tell. It's just, you have to.
I blame Johannes Bode, who is the person who chose the name. It's fine in German. Uranus. There's nothing wrong with it in German.
That's great. Yeah, ruins all the jokes, though.
Yeah.
All right. So, yes, they're ice giants for a very good reason, Duncan, because they've got ice in them in the atmosphere. But technically speaking, they are, in fact, gas giants. But
Yes.
and differentiate them because of their substantially different atmospheres. There you are. Thanks, Duncan. Great to hear from you. Great to hear from everybody. Thanks for sending in your questions. Don't forget, you can send in questions via our website, spacenutspodcast.com, spacenuts.io, and all you have to do is click on the various links on the right-hand side. Send us your question. That's audio questions only, or you can send us text and audio questions via the AMA tab up the top. It's your choice. Don't forget to tell us who you are and where you're from, and have a look around while you're on our website. Or join our media, social media platforms, Facebook, Instagram, YouTube, where you can subscribe just by pressing the subscribe button below, which, yes, it's down there somewhere. I don't know, one of those places. Fred, as always, thank you so much.
Pleasure, Andrew. See you soon.
Okay. Fred Watson, astronomer at large. We'll catch him on the next episode of Space Nuts. We might catch Hugh then as well, because not here today. Didn't even call in sick. I need a note. And from me, Andrew Dunkley, thanks very much for your company. We'll see you again soon on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.